Hello everybody, welcome to our second CPD webinar. We're going to be discussing site design considerations for radar systems. I'm Dale Jones, Business Development Manager for Navtech Radar. Quick introduction to Navtech. We're a UK-based designer and manufacturer of high definition radar systems, so based in the UK in Oxfordshire, and we've got almost 3,000 sensors now deployed out in the field, deployed globally, and the company sort of splits into three sort of separate divisions really. The first part of the business is the advanced guard business, which is more the security type applications using ground-based radar for surveillance. The Clearway side of the business developed radars which are used as safety devices for stop vehicle detection, collision detection, and that type of thing on highways, but also in tunnels and bridges. And the industrial automation side of the business, where we actually started, we supply radars which are used for things like autonomous vehicles, but also for automating industrial processes as well. As I said, we've been going for 20 years now. R&D is ongoing, and we're constantly evolving to meet the requirements of our customers. With very strong engineering background within the company, more than 50% of the employees are degree level trained or above. So what we're going to look at today is what things you need to be aware of really if you're thinking of specifying a radar for a particular application. So we'll go through a quick recap on how radar works and some fundamentals of the physics there, physical, environmental considerations on sites, and we'll finish off really with a bit of a case study on a project that we did with San Francisco Airport, which we would go through a lot of these types of processes. So first things first, quick overview of how radar sees objects. So basically, a radar can very accurately determine the range to an object. What we do is send a pulse of radio frequency or RF energy from the radar. That then goes out into space, and if it hits an object and reflects back, we can very accurately measure the distance of that object. And this returned energy is called an echo, just as it is in sound terminology, really. And what radar does is uses this echo to determine the direction and distance of that reflecting object. Because this energy travels through space in a straight line and only varies very slightly because of atmospheric and weather conditions, by using very special antennas, this energy can be focused into a specific direction. This then gives the direction, either the bearing or azimuth, or sometimes it's called, or the height of the reflecting object in question. And the time taken for the echo to return back to the radar, that gives us a very accurate measurement of the distance as well. Okay, so a few fundamentals really. I'll just show you a very short video. Okay, this is our demo site actually. Basically, radar can be used to monitor not just a site's perimeter and detecting intruders, but it's also got the capability to provide wide area surveillance, giving far better situational awareness to the operator. And as well as alerting operators to potentially multiple threats, radar can also determine the precise location of those threats, and then using advanced camera control functions can track them in real time for rapid alarm verification, as you can see on the video here. This detection and tracking is available day or night and in pretty much any weather as well. You can basically have as many alarm zones as you want, and each can be defined with their own very specific detection rules. And radar has also got the capability, as you can see here, to automatically classify targets based on their size and sort of behavior of movement, that sort of thing. As an addition to that, there is also the added capability to distinguish between friend and foe. So using GPS transceivers, that type of technology, we can identify all the security staff on site, for instance. So the system will still detect and track them, but it'll only generate an alarm if they enter an area where they're not authorized to be. So again, making the system a lot more easier for operators to use, and also filtering out any unwanted alarms as well. Modern ground-based radars is relatively affordable. As you can see, very easy to operate, and it's very readily integrated into many CCTV, VMS, and PSIM systems as well. One of the largest benefits of radar really is the fact that because we can cover such very large areas from a single location, and there's much less infrastructure required to protect even very large and complex sites. Just to summarize that really, so basically radar can simultaneously provide both wide area and perimeter monitoring with the same piece of equipment. It's all day, all weather capability, and when used in conjunction with CCTV can provide very effective alarm verification for the operators. It's easily integrated into other systems, and from an operator's point of view, it's really simple to operate. It's pretty much plug and play, leave it running really. And it's also complementary to other security sensors, but can also provide even more information, that including multiple target tracking and automatic target classification, so you don't have to generate alarms on things you're not interested in. Okay, another thing to consider really, there's a couple of different sorts of radar really. They're sort of split into two different types really. There's the scanning systems, which will cover 360 degrees. So you can basically cover very large areas, and that can be configured to detect intruders crossing a very narrow perimeter or between buildings, etc. And there's also the fixed radar systems, which again can cover very large areas, but if you do need to cover 360 degree coverage, then additional sensors will probably be required to cover the whole site. But they can be, a site would probably consist of a mixture of fixed and scanning radar sensors to cover all the different eventualities. Okay, so before we move on to actually designing the system, there are some basic principles that need to be understood first. And one of the most important of these is the resolution of the radar. This can have significant effects on how accurate the radar is, and also how effective it will be at removing unwanted targets. So resolution is a key feature really. So the range and angular resolution that the radar provides leads to something called the resolution cell or bin size. And this is if you compare it to a CCTV camera, it's like a pixel size in effect. And basically this defines the ability to distinguish two targets which are close together. And therefore the smaller this bin size or pixel size, the better the system's going to work, particularly for ground surveillance, where you need to detect movements very quickly. And you're generally looking at moving targets, although that's not always the case. So again, the size of the resolution cell, it is a critical factor to consider. Frequency also has an effect on resolution. As a general rule of thumb, high frequency radars tend to have much better range resolution than low frequency radars, which gives higher accuracy and lower false alarm rates. Okay, so basically every radar system works in the same way really. Every scan of the radar system will result in basically all of the fixed objects within its field of view are then mapped out into a thing called the clutter map. So this is generated in every scan. Basically what the software then does is remove that background scene from what the radar is seeing at that particular time, so that moving targets and new targets can be picked out very accurately. With very high resolution, it means we can process that information much quicker. Even high definition radars can't work miracles. So in an extremely cluttered environment like this, obviously any radar will struggle to identify any individual targets in that. Okay, so some physical considerations really on the actual site itself in question. One of the first and most obvious ones really is line of sight. All radar systems do rely on line of sight, so any buildings, fixed or temporary structures, trees, tall vegetation, etc., will all create blind spots. So care is needed in selecting the correct sort of mounting location, and also the best height as well. And the radar cross section of an object also needs to be considered. Even smaller, very highly reflective objects can have a significant effect on coverage. The term radar cross section, this is a term applied to it's basically a measure of the equivalent echoing area of a target. The RCS figure determines how much of the radar power that is transmitted onto the target is reflected back towards the radar. Radar cross-section doesn't always bear a simple relationship to the physical size of the target. Even very large targets, such as wind turbines, for instance, can have a very, very low radar cross-section because of the materials used in their construction and also the angles of that construction as well. Relatively small metal targets, such as posts, particularly very close to the radar, can create significant reflections, which may be powerful enough to mask any intruders close by. In this instance, this is where radars which can analyze the clutter more effectively will perform much better, particularly if it's a very cluttered environment. So going back to my previous point, really, the resolution size or bin size is very important. Okay, so on this particular example, we can see some very close into the radar. It looks like there's some metal posts or columns. It does create a shadow behind these objects, even if they're relatively small. If they're very close to the radar, they will have a bigger shadowing effect. So anything close in, such as trees, buildings, posts, that type of thing, can have a significant effect on the radar. So again, the location of that radar is quite key. Okay, ground levels. As we need clear line of sight, obviously if you've got sloping ground, then the radars need to be leveled to work along sloping ground as well. And we use a series of tripods with these radar targets. They're similar to the sort of thing you have on the top of a mast on a boat, which is highly reflective and very visible to radar systems. So we use something like that to line them up. Okay, this is a live example on a particular site. It's an airfield somewhere. You can see here potential intruders over near the fence line. They're actually partially obscured because the ground level drops on the other side of this road. So in this particular instance, it'd be a good idea to lift the radar up so that it's got a better chance of seeing down into this area. But because radar has got a very narrow field of view to the power relatively low and concentrate in a very specific area, but what we can do is divert some of that radar energy down towards the ground with a thing called a cosec lens, which can be added onto the radar system. What that does, it diverts some of the energy down so that the dead spot immediately below the radar is as small as possible, but it also means it can see much better into undulating ground levels as well, further away from the radar sensor itself. The actual ground surface that you're scanning across will also have an effect on the radar performance. Grassy areas in particular, as you can see from this couple of examples here, are much more reflective than tarmac or concrete surfaces. This is the raw data from the radar, and you can see the grass is a much brighter reflection than the tarmac and concrete around it. So it's very important that any system that's specified needs the flexibility to adapt or to apply different detection parameters to all those types of surfaces. This will affect the detection range of the radar itself. So on tarmac and concrete, for instance, we can detect intruders at much longer range than is possible on grass. And obviously it's also important to keep this grass cut down as well. Obviously, if the grass is particularly long, it can cause detection problems as with potentially masking the intruders. It's not so bad on this one because it's only sort of just above ankle height. But if it was above knee height, for instance, then the target presented to the radar would be a lot smaller. In windy conditions, as the grass moves around, it may produce actually false alarms from the movement of vegetation. So ideally, vegetation should be kept cut back. Or if that can't be done, then perhaps a change in radar specification or different location may be recommended as well. Okay, detection over water. Ground-based radars work just as well over water, really, and small vessels such as jet skis, canoes, and even swimmers very close in can be detected reliably in good calm conditions. However, the false alarm rates might rise in bad weather as the wave heights increase, giving rise to multiple reflections, which may cause false alarms, but also will cause variations to the detection performance and accuracy as well. So if you've got very large waves, boats can disappear behind these if they're severe enough. And it's also important to consider tidal ranges as well in these coastal locations. If you've got a very high range of tides, then you might need to consider having multiple sensors for the low tide and high tide water levels, because obviously the ground level in effect is changing between the two. We'll discuss this a bit more detail actually as part of the case study at the end. Okay, another thing to consider is reflection. So highly reflective surfaces, such as on this example here, I think this looks like a little fence compound down here, and you can actually see all the individual fence posts, which are very reflective, and they appear as very bright objects. These buildings over here, they're also very, very bright. Basically, if you've got a highly reflective surface, it can potentially mask an intruder very close to that object. Even in very high resolution radars, we can't filter out very bright objects. So if you've got an intruder standing right next to a fence, for instance, they might not appear to the radar until they move a little bit away from the fence. So anything like a metal structure or fence needs to be carefully considered. And it's also a good idea to make sure that a radar system doesn't transmit too much power for its environment. It's a common mistake we come across, really. People think that if they can put a more powerful radar system in, it's going to work a lot better. It can actually have a completely converse effect. So if you've got too much power and you're getting very high reflection rates, it will actually affect the detection capabilities on that particular site. So that's another thing to bear in mind. Okay, so moving on to fences themselves. These are probably the single most contributors to reflections on sites. Fences can have a profound effect on radar performance. They will generally cause reflections, and they will also attenuate the radar signal if it's detected outside the fence. And the level of effect will depend on the frequency of the radar that's used, and also the mesh size as well. If the mesh size is smaller than or very close to the radar wavelength that's used, the fence will act as a reflector, and targets on the other side of the fence probably won't be detectable. And in very windy conditions, a fine mesh can actually produce some motion induced sort of false alarms as well. If the mesh size is much larger than the radar wavelength, the signal will penetrate the fence. There will be some attenuation from the actual fence structure itself, and also any reflection that from the target outside the fence has got to go back through the fence as well. So you're going to get further attenuation there. So it's going to be much less sensitive seeing through a fence. We always recommend, if you want to see on both sides of a fence, it's always best to mount, similar to this application here, the radar directly above the fence, so that it's now got a clear line of sight of this whole perimeter out towards the marine perimeter, but it can also see inside the fence line as well, around the secure area. So always bear that in mind. So you can see a few examples here, really. So we've got a radar here, and you can see the reflection from the fence, pretty substantial there. So that reflection and the increased clutter around the fence may potentially mask some genuine alarms until they move further into the site. So the angle at which the radar hits the fence will also have an impact. So on this particular photo is taken from the proposed mounting location of the radar. So on this image, the radar can see all of the fence line. And if you look at that, even to the human eye, it almost appears solid as the distance increases, depending on the angle that you're looking at. So in that particular instance, we would get a very high reflection from the fence. But if you were to just move the radar mounting location close to the corner, you can see now the radar has got a much reduced view of the fence line itself in both directions, because obviously it's a scanning 360-degree system in this scenario. On the right-hand side, we would detect a person either climbing over or cutting their way through the fence much faster than the system on the left, where it's looking directly at the fence itself. Other things to consider, really, when you're looking at a system: target velocity. So basically, any specification should include the minimum and maximum speed requirements for detection of people and vehicles, for instance, and the capability to accurately determine target speed can significantly improve the target classification and tracking capabilities. The update rate, so how big's the area you're looking to protect. For big wide open areas where the targets are covering very large distances, then a scan speed of around about 1 hertz or 1 scans per second is usually sufficient to track even the most agile ground targets very reliably. If there's a requirement to track smaller, faster moving targets, particularly at relatively shorter ranges, then faster update rates are important. And also to detect within very narrow areas, such as sterile zones around a site, then both a narrow angle of detection and the faster scan speeds are definitely recommended. There's some specialist applications, things like drone detection is usually achieved with purpose designed systems covering very wide areas with very fast electronic scanning methods. And resolution, we've already discussed this. So basically, how accurately do you need to know the location of your target? If you've got a border and you want to know if a person is 5 kilometers away, for instance, you don't really need to know within a few centimeters where that target is. A few meters of resolution is fine, but on a shorter range site, such as a power station or an airfield or a VIP house, for instance, you do need to very accurately know the location of that intruder that's on that site, particularly if they're fast moving. Very precise detection is required, such as CP line monitoring on airports, for instance. Then the resolution of the radar is also very important to avoid both excessive false alarms, but more importantly, to avoid the possibility of any missed alarms in some of these very critical areas. So on this particular example, we've got a very narrow sort of sterile zone here, really, between the fence and the site itself. It's only 2 meters wide. So in this particular application, you're going to need a very fast update speed and good angular resolution to make sure you pick up any intruder crossing that line at speed. And because of the cross beam movement in this particular example, a Doppler radar, for instance, would really struggle to detect anything going directly across the field of view, because they have to change a distance from the radar set. They're reliant on a movement either towards or away from the Doppler radar. The FMCW radars work in a different way, and they will detect even stationary objects. Okay, this is an example of the importance of resolution, really, on an airport. So obviously on an airport, you've got aircraft operating, automatically classify the targets as they move in. And obviously on this particular environment, it's very important to keep people and aircraft separated from each other, so that they generally have things called CP lines, which you're allowed to move in the direction of the arrows, so a person can leave that area in that route. But as soon as they try and enter the area across that CP line, they will create an alarm. To avoid any false alarms, that line needs to be very tightly defined. And the same for these vehicles here. So a vehicle leaving the area won't be tracked, but a vehicle entering the area will create an alarm and will automatically be tracked by the relevant cameras. If we move on to environmental conditions, obviously site security radars, they operate outdoors, and they obviously need to tolerate much wider range of conditions than sensors deployed within a building, for instance. So any specification should include details of the environmental conditions that are to be expected on site, such as temperature, humidity, if it's particularly prone to bad weather, for instance, in which the radar will be expected to operate. And although radar is regarded as an all-weather sensor, heavy rain can actually cause some attenuation of the transmitted power reaching the target, and it can also produce backscatter of the echo that is reflected back to the radar system itself. It means that, again, there's less energy received, so it's important to ensure that any system that is specified has got enough but not too much power to get a usable echo from the target at whatever range is specified by the client, and also a well-designed antenna to allow adequate detection. As a manufacturer, we always quote very conservative ranges on our systems to make sure there's always enough performance in hand. It might also be appropriate to specify a desired level of performance. I'd, for example, detect a walking person at 100 meters in heavy rain, and actually give some figures for that as well. So radar will experience changes in their operating environments during the course of a day. So you've got daytime, nighttime, activity due to wildlife, on-site personnel and vehicle movements, for instance, and also seasonal variations due to leaf cover. So foliage itself, that also presents a particular problem, as it's obviously a barrier to radar energy. So you'll be able to see anything the other side of that vegetation, for instance. But it can also create unwanted alarms if in very high winds, for instance, as it's moved around. Foliage being blown around might appear as multiple moving targets. So obviously that all needs to be taken into account when designing a system. Okay, so that's an example of the effects of rainfall. So we've got a nice clear image this side with no rain. Over on here we've got really heavy rain, and you can see that the picture is slightly blurred. It's not quite as sharp, but as long as it's within the operating parameters of the radar that's installed, it should still detect. And we quote anything more than 50 millimeters an hour, which is really heavy rain. Actually, our systems will still work up to that type of level of rainfall. Okay, so some system design considerations as well. If you've got radar covering the whole of the site, it's also important that the CCTV coverage that's installed will also cover that site, so that any alarms can be very accurately verified using the CCTV images. Obviously, the radar will produce live target tracking information. It still needs an operator to verify whether it's a genuine target or not. Does it need a graphical user interface to show these live detection tracks on an interactive site plan? Quite often that's the case. It's also important to ensure that any PTZ cameras that are selected to provide this real-time tracking are compatible with the system you're looking at. With our system, for instance, any on-viv camera that supports absolute positioning can be controlled by our software, but that you would need to check that with each radar manufacturer. Also need to check that it's capable of being integrated with the system that's already on site. And to reduce any unwanted alarms, the system should also have the capability to define these very specific detection zones, each of which can have its own set of alarm filters, such as minimum and maximum target size, the speed, direction of travel, classification of the target, that sort of thing. And as I mentioned before, also the ability to differentiate between different ground surfaces. So the roads can have a different set of operating parameters to the grassed areas, for instance. Any system should also have the ability to set and unset individual zones from the operator's point of view, depending on site operating conditions. And it's a good idea to have a global change as well, which I'll discuss this a bit later on in the case study. So you can basically apply a global change for such as high winds or heavy rain, that sort of thing. So you can still keep the system operating at its optimum performance, really. Obviously, make sure it's expansion proof, make sure there's plenty of capacity for that. And part of that really is making sure that the network that is used has got sufficient bandwidth. We always recommend a gigabit network, not so much for the radars, but obviously you've got video streams running across that network as well. So just make sure you've got the amount of bandwidth that's required for the particular application. Consider the flexibility of the system you need, so and the ease of use for the operators. So and also to make sure, is there adequate security in place as well? So you've got password protection, for instance, on people changing things they shouldn't be changing, that sort of stuff. So think about what type of detection rules you'd need as part of that system. So obviously the more options you've got, the better it is, and more likely it's going to be to provide what the actual end user requires. Okay, when you're talking integration as well, what level of integration is required by the end user, really? Does the display need to be interactive within the PSIM or the VMS in question? Obviously consider the camera and also any other third-party sensors as well, which might be integrated into the system, such as audio devices, drone detection, or even alternate detection systems like a fence detection system, whether that can also be integrated in. This is an example of our system integrated into Milestone in instance, and within that there is an interactive site map, so the operator can change arm and disarm zones and that sort of thing. Okay, also consider when you're designing a system, how you're going to go about that really. As a manufacturer, we've got an online design tool which can be used, and we can give people access to that. What that enables you to do is basically get a Google Earth image of the site that you're looking at, draw in perimeter, locations of buildings and all that sort of stuff, and using that type of tool, it's very easy to sort of put together a very brief layout drawing, which can then be approved by the customer. Obviously, that's all based on data from Google Earth. If you do know a bit more information about the topography of the site, you can also take that into account. But obviously, there's never a substitute for a proper site survey. And as a manufacturer, we always go to site with the radars that have been potentially specified and test them in situ and produce a coverage report, which is then a written guarantee to the end user. So the end user knows what they're likely to achieve from that system. Okay, so some licensing requirements as well. This also needs to be taken into account. Most commercially available security systems that will operate, particularly in the UK, within the UK Office of Communications or Ofcom frequency licensing requirements. Even though that radar frequency might lie within a license band, there may also be some limitations on the power levels that can be used within that band, and it may still be necessary to get a license, even though it's potentially a license-free area. And in the UK in particular, civilian radar use, they're sort of centered around 24, 61, 77 and 94 gigahertz sort of frequency bands. For information on these frequency bands outside the UK, obviously you need to refer to the spectrum management of that appropriate national control authority, whoever that is. Radars can interfere with other RF equipment, and to a lesser extent, radar performance can also be compromised by interference from other external RF sources. In general terms, protective security radars generally radiate fairly low power, but obviously you need to clarify that with the manufacturer of the system to make sure it isn't a concern on the site. Scanning systems tend to be much lower power because the beam is concentrated in a much smaller area. They need less power to cover very large distances. Radars as active RF devices, there are limitations applied to the exposure of personnel to their radiation. Commercially available systems generally operate at very low radiated power, as I've just mentioned, but it is necessary to specify that the sensor meets any European safety directives for any radiation hazards within its specified operational envelope. Ours are safe from a meter distance from even the most high powered radar that we do, and generally, as they're generally up on a pole between 3 and 6 meters, that's not a problem. And any commercially available radar equipment should have undertaken the necessary safety certification, which can be provided from the manufacturer. Okay, so that's quite a lot to take in, really, lots of different things to consider, really, when you're looking at using radar. What I'm going to do now is just go through a bit of a case study we put together based on San Francisco Airport, where a lot of these types of effects were actually taken into account during the specification of the system on the site. Okay, so that's San Francisco Airport. As you can see there, it's a mixture of ground and marine perimeter on this particular site. The existing perimeter detection system they'd got was no longer fit for purpose. They'd got a CCTV system which covered most of the perimeter, but it was getting a bit old, and the ever-changing weather conditions on site regularly created challenges for the equipment and the operators of the system. Fog is very common in this area. In addition to this, the airport has also got 10 miles of waterfront perimeter, which can't be fenced for a mixture of things, really. One of them was aesthetics. They didn't want to put fences up, but also the aircraft operate very close to the edge of the site as well. So for those two reasons, it was decided they weren't going to put fences up around the marine perimeter at all. And basically, the San Francisco airport, they started looking at this very early on, actually, and in as early as 2015, they already understood that the future of security on site was more about using the right technology rather than using any physical barriers. And as a key part of the project, the airport authority included infrastructure improvements to support more advanced and future-proof technologies. Most importantly, any new system needed to be installed without affecting the airport operations. They couldn't close the airport at all to carry out any of this work. And these challenges led the airport authority to employ a specialist security consultant who'd already got extensive airport experience, and they also engaged with the National Safe Skies Alliance organization in the US, which had already conducted research into waterfront perimeter security. What they also did was contact some other airports with similar challenges. A couple of these were notably Schiphol Airport and John F. Kennedy Airport in the US. This extensive research early on helped develop the scope for the perimeter security project, and it was at this point that radar was highlighted as a potential solution offering. The wide area coverage that could be provided from relatively few fixed locations meant that any additional infrastructure was kept to an absolute minimum, without any compromise in the system performance, as well as providing the all-important all-weather day-night capability. What the consultants then did was they carried out a comprehensive needs assessment, which then really confirmed that perimeter security stood out as a major requirement on the site. And they then worked with various airport stakeholders to determine how the perimeter security needs affected everyday operational procedures. Very specifically, they identified that the airport needed a solution to provide accurate early detection and live tracking, particularly as intruders approach the shore and the airport. So they were looking for detection outside the actual the boundary of the airport. Radar, crucially, offers the enhanced capability to track those intruders, particularly if they do enter the airport's operating area. And the advanced situational awareness that this provides can be used to really effectively coordinate any response. There is a lot of movement on the waterway around the airport, and feedback from other airports was that this could potentially result in high false alarm traffic. So the design philosophy used is that when designing a perimeter detection, it's often better to use multiple detection technologies that complement each other, as every technology has got its own unique strengths and weaknesses. And based on this research, it was decided that layering thermal imaging cameras and radar gave the benefit of early detection and the ability and crucially the time to resolve these potential threats without affecting the operations of the airport. So radar is great for monitoring wide open areas from a fixed location, and the thermal imaging cameras, and the CCTV cameras make the operator's job of verification very quick and easy. And the analytics from the thermal imaging cameras then act to fill in any gaps that are left by the radar if there's line of sight issues from small buildings, that sort of thing, etc., around the perimeter. Okay, so what the consultant then did, they developed some evaluation criteria, and 2 of the 3 integrators that were bidding for the project were then invited to take part in a 2-part evaluation process The first of these was some static testing to evaluate false alarms, and then some test scenarios where they basically staged some attacks onto the airport. And the key to these tests was to set the detection threshold at the correct level. So minimum false alarm rates, but no missed alarms. So basically, San Francisco Airport, they approached the project in just the right way, really, carefully considering needs, clearly defining its technical and operational requirements, and developing a concept of operations to ensure that the operators can perform the security function properly. And in this case, the choice of the technology they actually used was the last, not the first step in the process. So they'd gone through a whole evaluation process first. And this basically ensures that the system as defined in the requirements was the system which was actually delivered to the airport. Ultimately, the airport, they selected a turnkey system that includes Navtech radars, color and thermal imaging cameras, and they actually use our advanced guard user interface as the security platform as well. One of the reasons for selecting Navtech was the high resolution capability offered by the W-band sensors that we use. They did look at they did actually try some alternative X and K band radars, which were also put forward by different integrators, but they just didn't have the same level of precision that was required to pick out these individual targets around the shore perimeter and in the cluttered airports around the airport as well. The false alarm rate was also the best they tested. With that, they actually achieved a 0 false alarm rate over the water level during the overnight static tests. In fact, it was so low, it was only during the actual test scenarios where they got some jet skis and some staged intruders that it was then confirmed that the system was actually operating properly. Another challenge they discovered during the trials was that due to the high tidal ranges in the area, some detection zones could either be across potentially choppy sea at high tide, or mudflats at low tide, which occupied by large numbers of seabirds and various other forms of wildlife, depending on the state of the tide. And as tides don't work to define time schedules, it wasn't possible to run different detection profiles, so based on timing. So it's critical to ensure that the system was flexible enough to work effectively in all these conditions and with different ground and sea levels. And the way we do this is by we now implement something called machine learning, and in combination with our extremely flexible detection rule engine, this means the system can automatically adapt for those changing environments to minimize the numbers of false alarms, but without compromising the detection capabilities, obviously just when it matters the most, really. And to fully automate the surveillance, the system uses multiple overlapping radars near the water perimeter that have line of sight views of the secure area, the shoreline and the airfield. And although there are security buoys posted around the perimeter, boats and windsurfers still fairly regularly pass into this secure area. And obviously these physical markers mean nothing to wildlife. And in this particular environment, early warning is the key, really. Okay, so the actual installation of the system took approximately 12 months, and it was carried out in stages, starting with the installation of fiber optics and power to support the new technology. The first radar units were operational in 2018, and the last ones came online in 2019. This strategy provided increasing protection of very large areas of the perimeter as the work on the infrastructure progressed onwards, really. And when the radar detects an object, the advanced guard system will classify it as either a person, a vehicle, boat, aircraft, etc., and then can apply some preset guidelines to determine whether that object is a threat. Multiple detection zones can be created, each of which have their own unique set of detection parameters, which can, as you mentioned before, can include size, direction, speed of movement, etc. So normal activity, such as an airport operations vehicle moving around a service road, will trigger a camera to follow that object, but it won't generate an alarm for the operator to deal with. A boat or a jet ski crossing the buoy line into the secure area, however, will again initiate the camera to track the target, but it'll also trigger an alarm that has to be addressed by the security personnel on site. And then cameras are automatically directed to track that intruder and continue to track them as they move across the airfield, and the system will automatically hand over to more relevant cameras if they move out of the range of the one that's currently tracking them. And overall, the airport's safety and security director reports he's very pleased with the system. He said the main challenge at the airport was the waterfront, where it's not possible to install physical barriers, and this system really mitigates that risk. Okay, so to summarize that, really, one of the key messages there really is the first one, really, which quite often gets overlooked. It's really important to clearly define the operational requirement that the customer has. It's also key to engage with key stakeholders at a very early stage, and also obviously environmental conditions must be taken into account on these types of sites. Also establish a very clear test plan with very well-defined acceptance criteria to protect the installer and the client as well, to make sure everybody gets what they're expecting. And basically, by using very considered design and detailed project planning, you can mitigate any impact on site operations as well. Okay, so that's pretty much it from the CPD point of view. I'll just have a look at some of these questions that have come up. There's one from me. I've got one about here about topography. If anybody has got anything else, as I say, you will be receiving an email with a link to give some feedback, and also to let us know if you need the CPD points as well. And if anybody wants the slides, we can send those out as well. Okay, brilliant. That's great. Thanks very much, everybody, for making the time to listen, and I hope you found it useful. Thank you very much.